In this video, we're going to take a look at just a simple example of showing how to compute the probabilities and the expected values and the standard deviation associated with a binomial random variable. So in the previous video, I defined what the experiment is, what are some of the hypotheses, what are some of the parameters, and some important formulas. But now we'll actually get to do an example. And I'm not going to do, for instance, a word problem, just a problem to get us used to the calculation, right? So here is the setup. So let's say we have a binomial random variable and our n is 10, right? And our p is 0.6, right? So again, n represents the number of independent Bernoulli trials. And again, that means each trial can result in one of two outcomes, success or failure. And this probability here is the probability of success, right? So just by writing this, the b tells me that it's binomial, right? So this tells me that it's binomial. And once I hear that, I know I have specific formulas. The first number in parentheses, that's always your n, number of independent trials. And then the second number is the probability of success on any of those, in this case, 10 trials, right? Okay, so let's say part A, we want to find the probability that x is equal to 3, right? So this is one of those probabilities where we're asked to find the probability that your random variable is equal to a specific number. Now for this, we have a formula for the PDF. So using the formula that we established in the previous video, it's this. So I'm just going to substitute the values right in. It's going to be 10 choose x times the 0.6 to the x power, and then times 1 minus 0.6 to the 10 minus x power. And again, what are the possible values of x in a binomial random variable? Well, it goes from 0 successes up to, in this case, 10, right? We can't observe less than 0 successes, and we can't observe more than 10 successes, right? So one thing I'll go ahead and simplify this difference, but this is our formula, right? It might not look like the type of function that you think of, when you're evaluating, but this is it, right? So 1 minus 0.6 is 0.4, and then we have the 10 minus x as that exponent, right? So yeah, it's just a matter of substituting, right? So what do we have here? So substituting it into this, then the probability that our random variable is equal to 3 is going to be 10 choose 3. And again, what this is saying, out of the 10 trials, we want to know like how many ways can we observe exactly 3 successes, right? And then times, and it's essentially our multiplication rule, but it's combined with combinations and now probabilities. The second factor here, the 0.6 to the third power, that's exact because of independence. We want to know exactly, what's the probability that exactly 3 of these 10 trials will be successful. So that's 0.6 times 0.6 times 0.6 because of independence. And then if 3 of them are successful, that means the remaining 7 of them, which is the 10 minus 3 exponent, those will be failures or unsuccessful. So we multiply all these things together and we're going to get our probability. So we know how to write down our combination in terms of factorial. So this is 10 factorial over 7 factorial, 3 factorial, and then we have our 0.6 to the third power times 0.4 to the seventh power, and then we evaluate that. And now I will write down, let me write down the exact fraction here. So it's 82,944 over 1,953,125. But as a decimal to 4 decimal places, we get 0.0425, right? So that's the probability that out of these 10 independent trials, each having a probability of success of 0.6, the probability of observing exactly 3 successes is just a little over 4%, right? Let's do another one of these. So let's say part B, we're asked to find the probability that x is equal to 6. Well, I mean, the setup is the same. It's just a different value of x now. So this is going to be 10 choose 6 times 0.6 to the 6th power, and then 0.4 to the 4th power. Okay? Again, so our 10 choose 6 is 10 factorial over 4 factorial times 6 factorial, and then again just multiply, so our 0.6 to the 6th, and then 0.4 to the 4th. And I'll go ahead and just give you the decimal for this one. It is to 4 decimal places 0.2508, right? And again, you can verify this one. So the exact probabilities, it comes down to, again, knowing how to handle our combination formula and simple multiplication, right? Next example, or next part of this one, so they'll all be with respect to this random variable. So let's see part C. Now let's look at something like a cumulative probability. So the probability that x is less than or equal to 4. Well, there are 5 ways that this can happen. X could be 0 or 1 or 2, right? Or 3 or 4, right? So these, again, are the mutually exclusive outcomes, all which lead to an x value being less than or equal to 4. And you might say, okay, man, I have to add up five of these things. What about the complement? Well, the complement would be worse, because if you do 1 minus, it would be 5, 6, 7, 8, 9, 10. You know, all the way from 5 up to 10. So it's like we're kind of right in the middle. So whether we look at the complement or not, we still have a lot of things to add up by hand, right? But this is where probability and statistical tables come together. There are many tables out there that give us the CDF values for specific random binomial random variables. There isn't a nice formula that could just sum it all up for us, right? Just because of the way the probabilities are structured, there's no nice closed form, what we would say formula to do this. So what I'm going to do is give you a glimpse as to what this table looks like, and then we're going to come back and finish this particular problem, right? So let me switch on over here, right? So hopefully we can see this table. Now, this particular table, the way it works, the far left column gives certain values of n. You can see it labeled right here. So there is your n. And then for each n, again, these are cumulative probabilities now. it gives you the specific values of x, right? Now, the reason why it goes up to 8 and not 9 is because if you have 9 trials, then the probability that x is less than or equal to 9, that is equal to 1. In fact, some of these probabilities, when rounded to 4 decimal places, are already equal to 1. So to save space in a lot of these, because it's a cumulative probability, we know we're going to end up at 1, so they eliminate an entire row. And what they're able to do is then include more values in there, more values that we don't know what the numbers are, so they can include more things in the table just by eliminating that row. Because we know in a CDF that those values, as soon as you hit the largest value of x in a discrete random variable, then the CDF values are always going to be 1. There are other values that could be 1 because of rounding, right? So in this particular example, let me take that off, our n is 10, right? So we're going to look in this group, and we're told that our p is 0.6. So the p values now are like the headers for the columns, right? So here's our p of 0.6. And you can see, just look at this table. I mean, this is a pretty decent table in that it has lots of different values of p. It doesn't have them all, right? But for a lot of convenient values, they're there. They're in increments of 0.05, right? So we got the 10. That's our number of independent trials. We have the p. That's our probability of success. And the question wants the probability that our x value is less than or equal to 4. So in this group, find the 4. There is the 4. And then go across to the column that has the 0.6. And there is our accumulated probability for us rounded to 4 decimal places, right? So this is the, let's say it all together. Or you can just listen to me say it, I guess. We have out of 10 Bernoulli trials, right, each with a probability of success of 0.6, the probability that the number of successes that we observe are less or is less than or equal to 4 is equal to 0.1662, right? So let's jump back to our other page now and write that in. So this, I will just say by table, right? So by our table, this comes out to be 0.1662, right? And you're certainly free, if you wanted to, do it by hand. I wouldn't recommend it. I mean, the table is there for a reason, right? I mean, it's great to evaluate these things, but you're not going to earn brownie points by doing a whole bunch of calculations that you don't necessarily need to do, right? So use the table when it applies. Now, when wouldn't it apply? Again, let's go back to our table. Suppose a problem gave you a p of 0.23. There's no 0.23, right? So the p values would have to be, like I said, starting at 0.05, going up in increments of 0.05 until you get to, I believe, let's scroll across here. Believe the highest is 0.95, right? So like if your probability of success is 0.99, then this table isn't going to help. Also, another limitation is the n, right? I believe there's another page to this table, and it may go up to like 20 or 25. But again, so if your n is like 30 or 40, again, this table wouldn't be helpful, right? So it just like any table of values, it can only hold a finite number of results that are useful. So if you get something that's not in the list of p's here, or not in the list of n's, then that's when you really don't have a choice other than finding some other table that might have it, or you might have to rely on software like Excel. Excel has these functions built in, the cumulative binomial and the exact binomial and so forth, right? But you can rest assured that either the p and n values that you'll be given will be in this table, right? Or they're numbers that you can add up by hand without having it be too tedious, right? So rest assured there will be a way to compute your probabilities. Otherwise, you wouldn't be asked to compute them, right? Okay, so there's that one. Let's look at another. Let's look at part D. And what if D wants the probability that your x is greater than 8, right? Now, this one, when you think about it, let's see, greater than 8 with a maximum value of 10, right? These discrete values of all that's left, it means that your x could be 9 or it could be 10. So here you do have some options because adding up these two probabilities is certainly a lot easier than adding up these 5, right? So we could do that. But just to give you another example using the table, I'll show you how we can do that. Now, because of how the CDF is defined, the table will give you probabilities that your random variable is less than or equal to a specific number, right? So what we would have to do is use one of our probability rules to convert this into something that has an inequality with less than or equal to. So the complement of x greater than 8 is x less than or equal to 8. So another way to write this probability is this: 1 minus the probability that x is less than or equal to 8. And this we can find in our table. So let's jump back to our table, right? So we want less than or equal to 8. So here's our 8. It's the same n and p. So there's our 8. And then we go over here. And hopefully you can see that 0.9536. So if we go back to our hand work, so then it's 1 minus 0.9536. We have to remember to do the 1 minus, right? Because we're using our complementary rule. And then this works out to be 0.0464. Right? So it's highly unlikely. Well, you know, there's over a 4% chance, not quite 5% chance, that we will observe more than 8 successes. But yeah, it's like, you know, if you're only repeating this experiment 10 times and your probability of success on any given trial is just 60%, yeah, it's unlikely, right, that you'll observe this many successes, right? All right, so that's D. And then let's look at like the mean and the variance and the standard deviation. So let's say we wanted to find the mean of this, right? Now in the previous video we looked at there's a specific formula, and I even gave you the intuition behind it. I didn't give you the formal proof, right? But again, I'm going to forego a lot of the formal proofs for these and focus on the, you know, what they are and how to use them, as opposed to the rigorous approach. But the formula for the mean of a binomial random variable, really easy. It's just n times p. It's just how many times you repeat this experiment times the probability of being successful on any given one of them. So this is your 0.6. So what we would expect is if there's a 60% chance of us being successful, and we repeat these things 10 times in 10 independent trials, then we would expect 6 successes, right? That's it. So that's our mean. Variance, again, equally easy formula. So that's our sigma squared, or if you want to use v of x, you can. But it's your n times p times 1 minus p. So we have 10 times 0.6 times 1 minus 0.6. Let me show the steps there. So this is 10 times 0.6 times 0.4, and that's going to give us 2.4? Yep, that should be 2.4. All right, so that's our variance. And then the standard deviation, of course, is the square root of this. And the square root of 2.4 is not a perfect square, or I should say 2.4 is not a perfect square. So when I go to take the square root of this, right? So again, let me write out the formula. So this is what you'll see and you can use. And then when you apply it, it's just the square root of the 2.4. So this I will round to, again, 4 decimal places just to be consistent with the rounding in our probabilities. 1.5492, right? So those are some important, like I would say basic but important calculations that are associated with a binomial random variable. And knowing how to use the table is a benefit. And our convention going forward is we will, whether you use the table or not, we will round probabilities like this to 4 decimal places, right? Now, if you have intermediate values, so if you're doing, let's say you're doing part C the long way, if you're gonna be expected to round the final answer to 4 decimal places, then you want to carry at least 6 decimal places in your intermediate values. That way you don't encounter too much round off error. And then propagation error. Propagation is that you round early and then you use those rounded values in subsequent calculations, and you just end up compounding the error over and over and over until your final result is way off, right? So it's a little tedious to have to do that, but in order to ensure accuracy, that's what we will have to do. All right. So hopefully you found that helpful. So go out and try out some binomial probabilities, and we'll see you in the next video.